lecture we will discuss the shortest path problem. Now, before we go into an algorithm to solve the shortest path problem, we will introduce something called a weighted graph. Now, we have already seen that a graph is an ordered pair of sets. So, I write G as a graph which is equal to V comma E, where V is the set of vertices and E is the set of edges. Now, we know what are vertices and edges. Now, when we have a weighted graph, then each edge has a weight, and in our discussion we will take the edge, the weights to be greater than 0. So, strictly speaking, we consider a function from E to positive real numbers So, we consider functions from E, the set of edges, to R plus, where R plus is the set of positive real numbers, and this function is called the weight function, and individual values of this weight function will be called the weights of edges. For example, suppose we have an edge E 1 belonging to E, we can operate the weight function on this edge E 1 and we will get W E 1, which is a positive real number and which will be called the weight of the edge E 1. Let us look at an example. Let us consider a graph like this. Suppose these are the vertices A, B, C, D and E, and the edges, suppose E 1, E 2, E 3, E 4, E 5 and E 6. Now, each edge are assigned to some weights, possibly the edge E 1 is assigned to 1, 2, 3, 5, 4 and 7. So, that means that W E 1, or in this case, since this is a simple graph, we can also say that W A B is equal to 1, W E 2 is equal to W B C is equal to 2, W A C W E 3 W E 3 equal to W A C equal to 3, W E 4 equal to W C E is equal to 7, W E 5 equal to W A D equal to 5, and W E 6 equal to W D E equal to 4. So, these are the weights of the edges, and this graph, which was originally G equal to A comma B comma C comma D comma E, and edges E 1, E 2, E 3, E 4, E 5, E 6. These graphs, when we consider the function W from E 1 up to E 6, that is a set of edges, to the set of real numbers defined as over here, becomes a weighted graph. Now, our problem here is that suppose I am given two vertices in a weighted graph, how do we find out the shortest path from the first vertex to the second vertex? And by the shortest path, I mean that a path such that if we add up all the weights of the edges belonging to the path, we will get the smallest value. If we look at the graph that we just drew over here, if we consider the vertices A and vertices C, and suppose we want to go from vertex A to C, we have got at least 3 paths. One is A to B and B to C. We see the total weight is 3. So, we have got A to B and B to C. A to B is 1, B to C is 2. So, the weight is 1 plus 2, which is equal to 3, the total weight, or otherwise we could have gone from A to C, the total weight is 3. Well, and the other possibility is from A to D, D to E, E to C. A to D is 5, D to E is 4, and E to C is 7. So, the total weight is 5 plus 4 plus 7 equal to 16. Now, of course, the shortest paths are this or this. Now, this is a small example and the graph is quite simple. That is why by observing the graph and checking the weights, it is possible to find out the shortest path. But it may not be so when the graph is complicated. We need an algorithm, and Dijkstra's algorithm precisely gives us that. So, to say, Dijkstra's algorithm gives us shortest path between 2 points. Now, we move on to Dijkstra's algorithm. Suppose we have got a graph where we are labeling the vertices by A, B, C, D, a small letter, and the edges from one vertex to the other by an ordered pair. So, now this algorithm finds the length of a shortest path from the input vertices A and Z. A and Z in a connected weighted graph. The weight of the edge I j is W I j, which is taken to be greater than 0. And the label of the vertex x is denoted by Lx Now, here in this algorithm, to each vertex we assign a label which initially keeps on changing and after that comes to a fixed label, and that label gives us the shortest length path, by which I mean the path for which the sum of the weights is the smallest, the shortest length path from the point A, that is a vertex A, to x, and these labels will keep on changing, and ultimately when we take the first input as A, that is we want the shortest path from the vertex A, and when we start calculating the labels at the end of the algorithm, the label corresponding to Z will give the length of the shortest path from A to Z. So, the labels are denoted by Lx. At the termination of the algorithm, Lz is the length of the shortest path from A to Z. Now, let us start discussing the algorithm. So, first step is input. Our input is a connected weighted graph in which all weights are positive. And vertices A and Z. So, we have got two inputs, so to say. One is the graph on which we would like to apply the algorithm, and two vertices in that graph between which we want to know the shortest path. Now, the output is Lz, which is the length of the shortest path from A to Z. Now, we come to the algorithm that we denote by Dijkstra W. This W is the weight function of the graph G that we are using, and A, Z and the function L, which we will see how to compute. Now, in first step we will put LA equal to 0, and for all vertices x not equal to A, L x is infinity. So, what we are doing in the beginning is that we know from our input that from which vertex we have to calculate the shortest path. We are putting the label of that vertex to be 0, that is that step LA equal to 0, and all the other vertices are labeled as infinity. Now, T is a set of vertices other than no, we leave it at set of vertices, and then we will process this T. Now, in the first step we come like this, that is while Z belongs to T, we start this loop, choose V belonging to T with minimum LV, and then remove V from T and build up a new T, and then for each x belonging to T, adjacent to V do Lx equal to minimum of Lx and Lv plus W Vx and return. So, let us see what happens. Our starting set of vertices is a set of all vertices, and then among that in T we find the smallest weight vertex, that is a vertex with the smallest level, and we choose it and then we delete it from T. So, then we will get a set of vertices other than that vertex that we have deleted. And then what we do is that we start scanning all the vertices which are adjacent to the deleted vertex, and then we will calculate this quantity. After calculating this quantity, now my T is changed. I go again into this and we again do the same process. So, this loop will keep on happening and this loop also will keep on happening. Let us look at an example to clarify this matter. This is A, then A is connected to B and the weight is 3, B is connected to D, the weight is 2, D is connected to G, the weight is 3, then B is connected to E, the weight is 4, and here AE, the weight is 9. Now, here A is connected to C and the weight of the edge is 2, C is connected to E, the weight of the edge is 6. After that, E is connected to G, the weight of the edge is 1. Now, E is connected to H, the weight being 2, and C is connected to F, the weight being 9. F is connected to H, the weight being 1, and here G is connected to J, the weight being 5, and GJ, the weight being 5 again, and here J is connected to L, the weight is 5, H is connected to L, the weight is 9, F is connected to I, the weight is 2, I is connected to K, the weight is 2 again, H is connected to K, which is 6, and K is connected to L, which is 3. Now, suppose somebody tells me that my input vertices are A and L, and I have to find out the shortest path between A and L. How do I start? Now, let us go according to the algorithm proposed by Dijkstra stepwise. In the first step, my T is a whole set of vertices of the graph, given graph. So, let us denote the graph by G. Now, and then what I do before that is that our starting vertex is A. So, LA is put to 0, L of anything else x is infinity for all x belonging to Vg minus L minus A. So, other than A, all vertices are put to infinity. Now, we start with T. Now, in the first step we will consider the vertex which has got the least label value, and in this case it is A. So, we will remove from T the vertex A. So, see A has the least L value. So, remove A from T. So, I calculate T, which is T minus A. Now, in that we have to consider all the vertices which are adjacent to A. The vertices adjacent to A are B, E and C. Now, we use the formula, that is, for all x, for each x belonging to T adjacent to V, Lx equal to minimum Lx Lv plus Wv comma x. So, this portion of the algorithm is to be used now. So, what do I do? Here my V is equal to A and the adjacent vertices are B, E and C. So, I calculate L of B to be minimum of L of B comma L of V, that is L of A plus W A to B. Now, we see that L of B is infinity and L of A is 0, W A B is 3. So, we have got a choice between infinity and 3. So, the minimum is going to be 3. Then L of E is going to be minimum of L of E and then L of A plus W A E, and using the same argument it is going to be 9, and similarly L of C is going to be 2, which is minimum of L of C, L of A plus W A C. Now, we see that now we have a graph where I do not consider A anymore. So, that is my new T, and B has weight 3, or sorry, B has label 3, E has label 9, C has label 2 and all the others have label infinity. Now, when we look, we go into again the while loop and we choose from T the minimum vertex, that is vertex with minimum label value, and that label value is going to be C over here. So, I can put the label of C to be equal to 2, incidentally label of A is 0, and then I will cut out C from T. So, now my T was T minus A, original T minus original t minus a, this is my t, and now my in next iteration my t will be essentially t minus a minus c. So, I will also delete c. Now, when I have deleted c, now I will calculate the new label values for the vertices adjacent to C. Now, what are the vertices adjacent to C? The vertices adjacent to C are E and F. Okay. Now, again we will come to this step. For each of these vertices we have to calculate this quantity. So, L of E. Now, we know that E has a label value that is equal to 9. So, I have to take the minimum of LE and LC plus W C to E. Now, that is minimum of 9 and LC is 2 plus C to E is just 6. So, I have to choose between 9 and 8, and which is of course 8. So, we see that the label value of E has decreased. So, we will put LE equal to 8 and LF equal to minimum LF, which is infinity, and LC plus W CF. Now, if we do LC plus W CF, then we have minimum between infinity and LC plus W CF is going to be 11. So, it is 11. So, now we come back to our original graph. We see that E is now labeled as level of E is equal to 8 and level of F is equal to 11 and level of B remains at 3, and we have cut out C. Now, we go to the next iteration. When we go to the next iteration, our vertices which we have to consider are B, E, F, and rest of the vertices are infinity. Among them, we see the B is the smallest. So, we have to start with B, which is 3. So, we are essentially cutting out B, and then we are recomputing the labels. So, B is adjacent to D, D is already infinity. So, therefore, this value LD is going to be 5, and when we come to LE, we will see that it is even shorter than before, and because if we go from A to B, that is 3, and B to E, that is 7. So, I have to compare between 7 and 8. So, this value of L is going to change to 7. So, I have got LE equal to 7 and LD equal to 5, and these are the vertices which are adjacent to B. So, after we cut off B, then again we have to look at the graph. So, I have got A, this is A, B, then we have D over here, then we have G over here, J over here, L over here, and C, F, we have E, and then we have H. H is connected to J, H is connected to K and F both. And now the weights, we see that this is 3, 2, 4, 2, 3, 5, and this is 1, and this is 5, this is 5, 3, 9, 6, 2, 2, here this is 9, and this is 1. Now, what we see over here, and this in between is 2. Now, what we see over here, that we have taken care of 3, we have taken care of 3 vertices. LA is of course 0, and we have found that LB equal to 3, LC equal to 2. These are not surprising, but because of our algorithm, we have come to understand that LE has a smallest value 7 and LD is equal to 5, LF is equal to 11. Now, if we look at this one, then we will see that if we look at this one, then we will see that now I do not have to consider BC, BAC. So, now I will consider the values of D, E and F. So, LD is 5, LE is 7 and LF is 11. Now, among these, of course, I will choose LD. So, I will take out LD. So, this also will go away, and then I have to find out the vertices adjacent to LD, adjacent to D, and calculate its L value. The only vertex which is adjacent to D is G, and its L value is going to be 5 plus 3, that is LG will be 8. And then, so I will go to the next step. Now, I will have I have to consider G, E and F, and when I consider G, E and F, then I am going to get E as the vertex with smallest level. So, this is the vertex with smallest level. So, I have cut so I have to cut out E and then consider the vertices which are adjacent to E. The vertices adjacent to E are H and G. Both in case of H, E is 7, so it is 8, and this is 7 plus 8 is 9. So, LH equal to 9. So, in this way we have to proceed, and if I keep on proceeding in this way, eventually I will get the L values of the other vertices. We have given L values of several, but let me list down. I will get LA equal to 0, LB equal to 3, LC equal to 2, LD equal to 5, LE equal to 7, LF equal to, it will come to 10, because we will find when we calculate from H, we will find that this is 1 and H is 9, 9 plus 1 is 10. So, LF will at one stage come to 10, and LG will be 8, LH will be 9, Li it will come to 12, LK LJ will be 11, LK will be 14, and eventually LL will be 17. And what is the root for 17? We will have to go to B, then from B we will come back to E. So, A to B, B to E, and then E to will go to H like this. From H we will have to come back to F. Yeah. So, F value is 10, and then from F I will have to go to I to K, and eventually K to L. So, we see that LK is 14. So, L capital L is going to be 17, and that is the shortest path. We have to keep on going through the iterations, and we will get this. So, this is Dijkstra's shortest path algorithm in action, and this is the end of today's talk. Thank you.